I'm Shovon Sengupta. I'm part of Fidelity Investment. I'm a principal data scientist there. So I'm here to share my perspective today on Trustworthy AI for the practitioners, specifically in the realm of finance. And the idea is to share, let's say, some kind of an. Okay, yeah, thank you. So the idea here is here to share an accessible definition of what is trustworthy AI, the pitfalls, how do you define it, and probably I'll try to conclude with a prescriptive framework for building trustworthy AI in the realm of finance. Okay. So I think it might be a good idea to jog up some of our memories around the key milestones of machine learning or AI, or what it means for us. So definitely, AI and machine learning algorithm touch our lives in many possible ways. But if we really have to think about it, it probably dates back to 1950, when the scientists were thinking around to develop some kind of machine which can think quite interestingly. And I think all these fields, right, rather as distinct inquiries of machine learning algorithm began to crystallize sometimes around 50. So somebody might argue that, okay, we had Alan Turing. Every one of us might have watched the film Imitation Game back in those days. But probably artificial intelligence or machine learning came to become a more prominent theme among the data scientist community, sometimes around 56, when in the Dartmouth Summer Research Project, the term artificial intelligence was first coined. 56 to 74, this era is a remarkable period where a lot of important breakthrough happened in terms of computational, statistical, or mathematical algorithms. And post there was an AI winter and stuff like that. So with this quick background, let me move to this central theme of today's presentation, that is the fairness aspect of it, right? So why do we think it is important? So it is no-brainer to claim that AI or machine learning is all-pervasive. It touches our life in myriad possible ways than we rather think of. But definitely, that's why this is the main reason why this era calls for a very careful, I would say, assessment and understanding of the risk and potential danger that might be associated with all these algorithms. And that's where the question of fairness or responsible AI becomes way more important. Why it is very much challenging, I'd like to draw some of your attention towards that fact, because it is no longer a purely social or technological challenge to solve with. It is more like a socio-technical problem, right? So which cannot be purely solved using only a specific type of technology or tools. And we need like a lot of diverse, myriad, I would say, things to deal with the question of fairness. Sometimes they are domain agnostic, sometimes they are domain specific. So we need to understand each of those critical nuances a little deeper. Now, when it comes to trustworthy AI, it's a very broad generic term. So we really don't know what to take out of it directly. Now, there are 6 big, I would say, building blocks of this trustworthy AI, right? So primarily it deals with the question of bias, the privacy preservation, reliability, purpose, fairness, and transparency. So I'll try to touch upon each of those components a little thematically. So the bias typically deals with definitely the algorithmic prejudices, which might cause a lot of structural bottlenecks or challenge in the machine learning algorithm. Privacy, yes, the lack of privacy, or broadly by privacy, we mean that individuals' ability to withhold information about themselves. So definitely privacy preservation is a very critical aspect of building a fair ML. Reliability. It typically deals with the epistemic uncertainties in nature as opposed to the aleatoric uncertainties, as they call it out. So without getting into too much into the technical definition of it, it basically deals with data drifts or concept drifts, those kind of challenges. Purpose, it is more about a philosophical consideration, like ethical practices associated with your ML learning, ML algorithms. Fairness, broadly, what I intend to refer here, it's a very big, broad definition. Anyone can think of like maybe 15 to 20 different definitions of fairness. But broadly, at least in the context of machine learning algorithms or deep learning, I'm talking about distributive justice or ensuring distributive justice for machine learning development. Transparently, this piece primarily deals with the interpretability or explainability of your machine learning black box models. And we will eventually sort of get into some of these components in our subsequent slides. Okay. Now we talk about a lot of these components. Now the big question is, how do we measure it? How do we understand each of these components in a little bit of detail? And at least we can come up with some kind of prescription to measure them, because without measurements aspect, none of these concepts are going to fly, or at least help us in bigger way. For bias, as I said, like this false discovery rate or average odd differences, these are some of the most popular references. So it doesn't technically mean that this is the exhaustive list of elements that we can technically cover here. For privacy, this is rather, I would say, an unsung hero in this entire game of fairness analysis, because privacy preservation is very important, like when you are dealing with sensitive data, PII data. So the form of anonymization that we can use is very critical. And fortunately or unfortunately, this is an evolving space, but we do not have, like, let's say, too many functionalities available these days. That's why I just have explicitly called out a few more here, which are like the Python packages people can refer back. Reliability, yes, min-max robustness is one such popular approach. For fairness, we will again delve deep. We'll see like there are probably quite a bit of measure available these days, and which can people use to ensure that their machine learning algorithms have certain amount of fairness quotient involved into it. Transparency, again, this is beyond the scope of today's presentation. It requires, like, it's a very broad service that's being developed every day. By the time I conclude today's presentation, probably a few more additional metrics will be added into your arsenal. And yeah, so with this, I'll just quickly move on to the very first element. So we're talking about bias. Now, where does it originate from, right? So what do we typically mean by this bias? Now, I have categorized them in three broad levels. One is called the sample bias, which is typically originating from the fact that certain categories or populations are being either overrepresented or underrepresented in your training data sets. The label bias, which typically originates from the fact, like some kind of bias associated with the annotation services. And the third one is outcome proxy bias, which is more about the misspecification that may be present in your data, or in your machine learning model, sorry. Now, this is a rather complex slide, sorry about that. So here it actually talks about the typical algorithms for bias mitigation. So we have talked about how, you can, where and how this bias can come into your system. Now the question is how to mitigate them, or how to address some of these challenges. Now this address process can happen in several stages. Either in the overall ecosystem of your machine learning model development, it can happen at the pre-processing step, it can happen in the in-processing or the during training phase, it can happen in the post-processing, like after you have developed the model, it can happen at that stage as well. Now there are several measures depending on at what level you are trying to address them. So pre-processing, in-processing, and post-processing. I'm not just kind of iterating through or navigating through each of these components. It's there for your view. But some of the popular ones I would definitely like to highlight. The reweighting ones, which is one of the most popular pre-processing approach. The second one, which is technically my favorite, which is the in-processing algorithm. Although I do suggest people that it is probably better to address this bias mitigation aspect maybe in the post-processing phase once you have developed the model. It's comparatively easier. So the one that I was going to highlight, like, so my favorite, like, again, without any personal bias towards it, that's a prejudice remover. So it is just about introducing a anti-discriminative regularization term add to your loss function of your machine learning model and recalibrate the model using that loss functions. Some of the other very popular measures which can be broadly classified under post-processing algorithm is the ones for equalized odds or calibrated equalized odds. So we'll just come to some of those concepts a little later on. Okay, here is the one. So we talked about bias. Now the big question is, how do we sort of measure it? And these are, again, it's not kind of like a very laundry list of measurements. It's not all exhaustive, but definitely the ones which are quite popular. So here, like, disparate impact or statistical parity difference is probably one of the most prominent ones. You'd eventually discover that the bottom part of it, right? So here you probably find some of the measures which typically deals with privacy preservation. So one might wonder, like, why do we have some measures which are for privacy preservation and fairness, because sometimes fairness is, I would say, an intertwined concepts along the privacy preservation. So this is one of the critical block for them too. So that's why, I just exploited the opportunity to mention them or highlight them here. So we talked a lot at some length about how do we measure bias and what are the key metrics and stuff like that. But it would rather be unfair if we don't sort of share something on like how do we measure it, like without being bogged down, like what do you find these measures, right? So I have I've taken the liberty and highlighted a few important and notable mentions, I would say, like EIF 360. It is all fairness, and then FairML, ThemisML, and FairTest are few notable ones that I just highlighted. Along with that, Fidelity has also joined the league. We have our own developed package called Jurity, which is basically the one that for different sets of fairness metrics on recommender system as well, which definitely covers a hell lot of ground in terms of dealing with the fairness measurements. But again, this is not the laundry list. There are many other good packages out there these days. Something quite a bit new are getting developed these days. But these are the ones which are quite foundational, and I would rather highly recommend to explore some of them to see like what are the different metrics that they're providing. So they're quite rich in terms of their offerings as well. Okay. Now, what is the exact problem at hand that we are aiming to solve through these fairness questions? Because we understand fairness is important, but what happens if we do not have fairness in place, right? And that's where the game becomes quite critical. So I have highlighted a few key elements like favoritism, quality of service, denigration, stereotyping. You'd see a few glaring examples in subsequent slides too. But all these components sometimes raises a lot of questions around the ML models or some kind of suspicion around them, because people are not either very comfortable, it may be because of lack of their information, or it could be the real problem associated with these algorithms. And that's where this checks or guardrails around all these mishappenings comes to place, and that gets included into the fairness question as well. For example, one glaring example I can highlight, like it's an interesting one, which is from the Bloomberg News analysis. They reported that 6 major cities, revisited by the Amazon Prime service, purposefully or some other measures, right, excluded predominantly the black zip codes from servicing them through. And it was quite interesting to know that it was their algorithm that did not probably understand why it should should not do that. But it was an kind of a glaring interesting examples that got reported in one of those reports by Bloomberg News Analysis. The second one, this is always over and under representation, right? So the skewed image search results can always give an important example for this harm. And machine learning algorithm can simply introduce this kind of bias quite, I would say, unwillingly, and the data science practitioners may or may not be, in a position to address them right away. But it is important to be aware of this first before you can address it, right? Stereotyping, or it's another probably the most popular, I would say, pitfalls people are aware of, like stereotyping gender views. Say, for example, one interesting example I just came across, right? So it happens all the way through machine translation and all. The Turkish is a genderless language. It has got I'd say, a single pronoun O to indicate like any single third person. But when you are translating, let's say, she's a doctor and he's a nurse, it gets automatically translated back into he is a doctor and she's nurse. So this kind of gender stereotyping is quite popular. We inadvertently sort of miss this out, but they're the part of our reality. So as you can see that this is not desirable at all. Apart from being wrong. Denigration. So there are another interesting examples, right? So where one classic example of denigration is this Nikon's face recognition algorithm. So where they mistakenly flagged a lot of Asian people as blinking at a much higher rate than for other demographics. So people are thinking that, okay, Asian people are probably blinking. So it is. I mean, what exactly went wrong into the algorithm is difficult to know because it's more like a black box for for both us and for them. But this is one particular example of denigration that might slip in through your system, where too much homogeneity leads to some kind of unfair treatment. Okay. Now, all these examples, it is important now to understand like what actually fairness is, right? So when you talk about fairness, we're talking about definitely algorithmic fairness and nothing fairness in other aspects, right? So it broadly relies on 4 key principles: equality, equity, security, and privacy. As you can see, the privacy is also one such, I would say, constituting element for creating fair, I would say, machine learning algorithm. Now, there are a wide array of measures. If someone is trying to define fairness, probably somebody might encounter like 15 to 21 different definitions of fairness, right? And but at least I have kind of highlighted a few. This tree diagram talks about broadly the rationality-based and awareness-based fairness. So in the interest of time, I cannot go much beyond that. I think I'm more than happy to discuss after this session if there is an interest around it. But going in much detail would be overkill. That's why I'm just kind of skipping. This one aims to summarize some of the measures that we talked about. Please do not get bogged down too much about this mathematical expression. So here we are talking about a learning process, which is denoted by the function fx. X is the the attribute sets, or the input sets, famously called. S is the one, the protective, I would say, attribute, which might be like a gender, race that you are going to sort of use as a protected entity. And y hat is basically nothing but the predicted outcome of it. So each of this definition goes through it. So demographic parity, I just like to sort of call out, right, since I mentioned it before, that it requires that both targeted, or rather both protected and non-protected segments receives equal predictive outcome with similar probability score. So there is not much discriminations around that. So this is one very, I would say, popular approach to sort of ensure algorithmic fairness. It is being used across different disciplines as well. But again, having said that, is not the only one. And since, as I said, that there is no uniform, universal definition of fairness that people can come up with, and that's why we need so many diverse types of measures to deal with the question of fairness. Now, I mean, large language models are kind of very pervasive in nature, right? So now, I believe even in this conference, almost 60% of the presentations or discussions were around large language models. So here I just wanted to draw your attention towards one such particular examples where large language models are quite vulnerable to this kind of fairness questions or social biases, which might lead to certain kind of representational bias, which might have a very hazardous influence on the nature of the language generation process we may have into system. Now, GPT, again, it's rather a predecessor of our current GPT-4 model, which is generative pre-trained models that we have. GPT-2 all that talks about. So this particular reference aims to find out, to detect this kind of social bias that might be present in the entire natural language learning process, and figure out a few metrics to assess them, and then it went on providing a clear-cut prescription around how it can be mitigated. And some part of this are also associated with the hallucination aspect that we are seeing for GPT-4 or a few other large language models that are being increasingly used in many disciplines and many operations. And the next one, this is more like a quick blueprint for developing a fairness-aware machine learning pipeline for Fintech, so which broadly defines around it. Starting from the reading the data, it basically plays around 2 key concepts. The first one, developing a calibrated classifier mechanism, and then introducing an adversarial components to readjust or reweight some of the labels which might be misclassified and under the influence of unfairness or some kind of considerations over there. So with this, I think I'm just the penultimate stage of my discussions or presentation. So I would love to echo probably one of the mightiest statisticians of 21st century, George E.P. Box, who famously sort of said in one of his writing that essentially all models are wrong, but some are useful. The interesting part is we are not here just to find the useful models, but to find the one which is just, relevant, and trustworthy. And yes, with this, I just kind of rest my case. And yeah, thank you all.